Do we want to give it a couple minutes or are we ready to get started?
Let's just go ahead and get started, I think.
Yeah. So, this is the fourth session, and today we're going to deviate slightly from the original kind of schedule that we had laid out to incorporate a session on the EMA, and we're going to start out with Mark giving an introduction and some of the theory behind it, and then we will jump into the demo code from that point. So, Mark, do you want to take it away?
Yeah. Okay. So one of the, I think, fundamental concepts of today is going to be the EMA, and why the EMA is there. We've actually got two of them, and I'm going to go into precisely why that's there. And I think that it's a natural follow-on from the class that we ran last time, because the EMA is intimately related to trading and price quoting, and it's also critically important for preventing exploits in the protocol. And I think that it's just a really good opportunity to explore some of the design aspects that go into these systems, especially for anyone who is watching these on YouTube or attending these calls to inspire their own protocol development or something like that. And so what I've got here in Excel is basically just a random program that's just simulating an arbitrary number of swaps, and those swaps are causing the spot price in the pool to change. It's also recording a time difference, and what this chart is showing is how the spot price on the pool is evolving over time, and then each one of these traces is a different kind of moving average. And so there are a couple of things that I want to bring your attention to before we get into precisely how these things are calculated and why they're calculated that way. So this blue line, is that showing up clearly, by the way? Can you guys see my screen okay?
Yep.
Yes.
Okay, great. So this blue line is essentially monitoring every single swap in this fictitious pool, and you can see that it's moving around on every trade, which is precisely how AMMs operate, right? Every single trade will cause some impact on the price, and so the problem with this is that MEVs and miners in general, or even just nefarious influences in blockchain, they can use these this behavior of AMMs to perform very sophisticated attacks. Some of those attacks are known as flash loan exploits, or sometimes oracle exploits if that pool is being used as a price feed for some other feature. And so this is kind of I've programmed this one to be relatively gentle, so you can still see it's very fuzzy, very noisy, but this is not out of the ordinary, right? There's nothing especially bizarre about how this price is performing. But we can never know for sure, right? It could be that some of these sudden spikes up or down is because someone is trying to move the price in the pool to achieve some sort of malicious goal. And so there have been several attempts in the industry to introduce different ways of handling the price impact on a pool and how it influences the protocol itself or other protocols that are dependent on it. And one of them is to use something like a 10-minute simple moving average, and that's this gray line here. And you can see that it does a pretty good job at sort of smoothing out some of this noise, but it's always lagging behind, right? In quite a profound way, actually, and that's just because it is a lagging low pass filter. But you do get a nice smooth line, which is nice, and so it's very good at indicating a trend. But what it's not very good at is telling you what price you should trust right now. And this is, in my opinion, one of the things that's been badly implemented in a very large number of protocols. And so this time-weighted average system, which is very, very common, it's really good at telling you how the price now compares to how the price was. And so you can use that information well. Like, don't get me wrong, these systems can work well, but they're often implemented naively. And so a good way of looking at this is that you can see, for example, during this capitulation, the moving average, right, the simple moving average, all it's telling you when you look at it and compare it to the current price is that the price used to be high, right? And so simple moving averages, when you're looking at especially chart analysis, it's really only good for telling you whether or not there's a trend. So whenever the simple moving average is above the spot price, you know that that spot price is currently in a downtrend. You can see here that the simple moving average is still high, so it's not even very good at telling you what the trend is. And that's because a lot of this noise here, right, there is still these spikes downwards. And so the simple moving average is kind of failing to indicate that the price is actually in an upwards trend. So simple moving averages have like very severe limitations, especially when you've got, time resolution on the scale of a single block, which is about 12 to 14 seconds for Ethereum. And so another thing that you can do is you can change the way that simple moving average is implemented. And so in protocols like Bancor version 2 and Bancor version 2.1, there was an adjusted simple moving average that is really what its goal is to try and report what price you would be confident in, essentially. So it's not trying to indicate a trend, but it's trying to basically draw a smooth line through the data. So that if you were to ask the pool, what is the current price of this token, that it's not out by 5% or 10% just because there's been a sudden jump in the price. And you can see that this orange line, which is the one that we used in Bancor version 2.1, it's actually doing a relatively good job of that, right? It is, it does have the problem of it currently, it can undershoot the price. So, for example, during this move here, you can see that there's a very clear trend in the price here, but the simple moving average is kind of lagging behind it. And in general, this is kind of true all the way through the data. So even though it's better than the true simple moving average, it's still imperfect, right? And you can see, especially here, it's actually doing an even worse job compared to the true simple moving average of indicating sort of where the trustworthy price, if we want to call it that, actually is. And so with Bancor version 3, we've introduced the EMA, which is a shorthand for exponential moving average. And this is kind of a very badly defined term anywhere, actually. There are a very large number of ways of implementing it. And what we have is what I think to be quite an elegant solution, and I'm going to show you precisely how that works in just a minute. But before we do, I just want you to have a look at the profile, right? So you can see again, the blue line is very noisy and moving all over the place, and see how well the yellow line is tracking it. Okay, like it's actually, if you were to give someone a crayon and ask them to draw a smooth line through the data, this yellow line, the EMA that we've developed, it's actually doing a pretty good job of indicating that, right? It's not really biased towards a trend. You can see it follows this capitulation a little bit better, but it's still conservative, right? It's, even though it's lagging behind, it's still, occasionally touching these correct price points. And so, if someone was to ask you what the current price is right now, using this yellow line, it's actually giving you a much better sort of indication of what the aggregate result is, in a sense. And so I've drawn a second chart here that just has the yellow line drawn through the data, so you can see it a little bit more clearly. But yeah, the point that I'm trying to get across is that this EMA, what it's trying to do is to report a reliable price, something that can't be easily manipulated by, for example, a flash loan attacker that could use that advantage either against the protocol or against another protocol. Okay, and so I'm going to show you how how this is implemented. Okay. So, let's just start a new tab here. Okay. Actually, I've got it already up here. Okay. So, how this works is that we're going to be using, time to track the simple moving average, but for the exponential moving average, we're actually only going to be tracking the change in the price. So essentially, this is how this works. And we'll start a new one. So let's say that we have a spot price that's going to be moving around. So let's say, let's just do a trend here. Let's say the spot price is going to be 1 in the first instance. Oh, my machine is running so slowly. Sorry about that. And let's just say that every block is going to increase by 10%, which is going to be a huge exponential move, but that's okay. Okay. Now this is how the EMA works. The first thing that you have to know is that when the EMA is initialized, it takes on the same price as the spot price. So this is important because when a pool begins, the EMA and the spot price are exactly equal. Now we use an alpha value, and I think we set that to 20%. How this operates is that the EMA, it will never change. It will never change at the time that a trade occurs, right? It will only, it's lagging in the sense that it refers to itself and the last price in order to update its current price. So think of it this way. When you perform a trade on Bancor version 3, the protocol will have a look at what the current spot price is in the pool before your trade occurs, and then it updates the EMA before it processes your trade. And this means that on any trade, because it's always updating based on the previous trade or the previous state of the protocol, it means that trade itself can't be used to adjust the EMA. And that lag means that it gets much more difficult for an attacker to perform an exploit. It's not impossible, but it's extremely risky if they're going to do it. If we're using one EMA alone, I'm going to show you in a second how a second EMA makes it absolutely impossible for an attacker to do this. Okay, so let's have a look at this. The first thing that we do is we multiply this alpha value by the spot price, and then we multiply 1 minus that alpha value by the EMA. Oh, sorry, it's actually the sum of these two things. Okay, and I'm just going to quickly wrap the alpha value in dollar signs because that alpha value doesn't change. Okay. So you can see that based on this logic, the EMA is exactly the same, even though the spot price is moved. But when we drag this down to the next cell, you can see that the EMA is going to start updating itself. And so this cell here is really referencing the two cells above it. So you can think of this as is what was the EMA on the previous block, right, or on the previous trade. And so as we move down here, we can see how this thing is moving up. And so if I quickly graph this, you'll see that we'll have very this up. Okay, so if I graph these things, okay, what you can see very, very clearly is that the EMA is constantly lagging behind the spot price, right, which is what we want. Now, what I want to show you is that if one of these prices suddenly became much, much larger than the other prices, because of this resistance to price manipulation, the EMA shouldn't move very much. So let's say that, during this trend, one of these cells actually sort of doubled in price. Let's change the formula from there, for example. Okay, so you can see, if I zoom up on this, that there was this very sudden change in the spot price. But the EMA basically didn't refuse to react to it, and that's by design. And so if we now copy paste, let's do it this way. I'll go back to how it was, and I'm just going to copy these values. Okay, so they're no longer formulaic, and I'm just going to set one of these values to be, I don't know, 100 times bigger. And what you should see is this huge spike in the spot price. And this is exactly what a flash loan attack would look like. And what you're seeing is that during that flash loan attack, right, the EMA fails to respond. And so if the attacker was hoping to exploit the protocol or use the protocol to exploit some other protocol, because of the way that the EMA basically ignores this value, he's not going to be able to do that. But you can see that in the next EMA update, it still moved significantly out of range and then only slowly drew itself back. So this particular weakness in using a single EMA still means that you can perform an exploit if you're relying exclusively on a single EMA. What I do want to point out though is that if this was a single block in Ethereum, okay, so if the attacker was trying to perform their exploit sort of during this move, they would have already missed their opportunity, right? And this is what I meant when I said that it's an extremely risky thing to try and perform this exploit, although not impossible. And ironically, it's actually one of the things that was worrying about Ethereum after the merge, is that being able to control 2 consecutive blocks, which is what I'm trying to depict here, becomes a lot more convenient. And we've already seen some of these products start to surface that can perform, for example, a flash loan over multiple blocks. And that means that these kinds of price attack manipulations and any of the consequences thereof are likely to start becoming more and more familiar, unfortunately, after Ethereum merge. And I'm hoping that some of the precedents that we've set with regards to how to handle it might actually inspire some of these protocols to adopt slightly more robust procedures. What I also want to point out is that the EMA that we're using here, notice that it has no time component. It's only looking at what's the change in the spot prices and its alpha value. This is also really important. On Ethereum, it's not necessarily such a big problem because the clock on Ethereum is pretty reliable. But on some layer 2s, it's actually possible for miners to collude to adjust the time. And that means that any moving average that is time-based it's possible to attack it if you've got control of the network, or if you're collaborating with another miner, and the two of you agree to advance time in a way that is unexpected. So what I'm going to do is I'm going to share a program that I wrote, which actually exploits Bancor 3 using the single moving average. And then what Mike is going to demonstrate is how our implementation of the dual EMA prevents this exploit from occurring. So I know that this is really small, so let me zoom up on this. So I can, if anyone's interested in how I did this, you're welcome to contact me. I can share this function with you. I was actually checking with Mike earlier on the call. The exploit function is actually built into the simulator. It's called trade to EMA. It basically is performing this precise EMA manipulation on a single EMA. It's emulating what it would look like if someone was attacking the network. So it's in there if you want to use it. And that's something that we'll look at, I think, when I give the floor over to Mike. And if it's not a part of the main branch, then we may consider adding it to the main branch or something later on. But here we've got basically, the starting state of the system with 100 BNT, 100 TKN. The spot rate, of course, is 1. The EMA is 1. Let's pretend that this pool was just recently initialized. And I haven't spoken yet about the inverse rate or the inverse EMA, but that's going to be coming up in just a second. We've also got a swap fee, the network fee, and I've just included a column here that says, what are the actions being done. The first column is the block number. And this is the thing that I want you to pay attention to, because this is what I meant when I said it's not impossible to perform, but it is actually very difficult. So in the first block, what our attacker is going to do is they're going to trade a very large amount of BNT. And you can see in my readout here that the attacker has swapped 10,000 BNT for 98 TKN. Okay, so and swapping 10,000 BNT on a pool that only has 100 BNT in it is pretty catastrophic. So on that particular block, they managed to move the spot rate from 1 to 8,000, which is huge. It's an 8,000x change in the price of change in the price of BNT. But remember, I said that the EMA, it's always lagging behind. So when this EMA was calculated, it's only referring to the previous EMA rate and the previous spot rate. So this is demonstrating that, performing this attack on the same block, it's not going to achieve anything, right? The EMA refuses to acknowledge that the change in price has occurred. But at the beginning of the next block is when it's going to start taking that price change into consideration. So let's say that there hasn't really been a change in the price of BNT and TKN. And so what the attacker here has done is they've opened an enormous arbitrage opportunity. Okay, but they began performing this attack on the first block. If they now control the second block, what they can do is trade some of this TKN back for BNT. Okay. So now what you're seeing is some of this BNT they're buying back from themselves. They're partially closing that arbitrage opportunity. And that's going to bring the spot rate and the EMA rate into balance. So essentially what the attacker has done is said, okay, I know how the EMA works. I'm going to move the spot rate, and I know that the EMA rate won't change. But when the EMA does change on the next block when I trade, I'm going to trade the spot rate back down to wherever the EMA rate is going to be. Right? This is exactly how you would perform that exploit. And so if they control both the first and second block, then they're able to do this. Now, the second action that they take on the same block as this one, you can see that the block number 2 appears twice. So this is something that they need to bundle together. After they've performed this trade down, what they're going to do is they're going to add some liquidity. So you can see here what they've done is just added a single way of whatever that token liquidity is. We're assuming in this case that there is plenty of off-curve liquidity in order to, that's able to update according to the logic of Bancor 3, which in this case limits how large the pool can grow by 2x. So you can see after they've deposited that one way of liquidity, it's taken some of those off-curve tokens and updated the BNT balance to be almost 9,000, and it's updated the TKN balance from 2 to 5. And the protocol would allow this if it only had this spot rate and EMA rate to go off, right? Because if it's just comparing these two numbers, it's going to say, yeah, the price looks relatively stable, go ahead and perform this action. So after the protocol updates these balances, now what the attacker has essentially done is added a very large amount of, they've caused the amount of BNT in that's available to them to arbitrage to double. And so their last action is to then arbitrage this pool back to its starting spot rate, or at least nearest to its starting spot rate. So they trade their tokens back in, they extract 8,000 of this BNT, and now there's no arbitrage opportunity left in the pool. There's only a arbitrage opportunity left on the pool. The EMA is way out, obviously, but that will adjust over time. And, if they started with, 10,000 tokens of each, then by the end of this process, they've spent about 123 TKN, but they've gained like 4,000 DNT in the process, and so their total exploit value is about 38%. Okay, so this logic is obviously flawed, right? If you can demonstrate that this exploit can occur, then someone else is going to figure it out and perform it. So what Bancor 3 has introduced that keeps the system time independent is what we call an inverse EMA. And this is the thing that I want you to pay attention to. So if we go back over these steps, we can see that the trader moved the spot rate up and then moved the spot rate down to match the forward's EMA rate. But look what happens to the inverse EMA over those same steps, right? The inverse spot, right, goes from 1 to near 0 and then back to 0.01. And the inverse EMA, which is lagging behind, goes from 1 to 0.8. And this is the point. When the spot rate and the EMA rate match after an exploit like this, the inverse spot and the inverse EMA will always disagree. And this is just a consequence of the fact that if you're moving the numerator on any fraction, you can move it anywhere between 1 and infinity, right? If you've got x divided by y, if you're changing x, that fraction can be made an arbitrarily large number. But if you're changing y, it can only move between 0 and 1, which is interesting. You've only got this very tiny amount of space to move, the absolute value of a fraction if you're changing the denominator, but if you're changing the numerator, you can change it an arbitrary amount. And so as long as we keep this linear, right, and it's deliberate that the method that we're using here is arithmetic rather than geometric, because it means that the inverse of a fraction, as you average it, will never equal the average of the forwards fraction. So this particular exploit actually is impossible to perform on Bancor 3. And it also means that if someone was to use the pools as, for example, an oracle, which is very common, they can see both the inverse EMA rate and the forwards EMA rate. And so if, for example, this is going to be used to trigger a liquidation or report a price for any other kind of use case in DeFi, the fact that the EMA rate and the inverse EMA rate don't agree with each other, or that they have some huge significant deviation, is, as for our use case in protecting the protocol against exploits, it can also be used to protect other protocols against exploits. And the fact that it's time independent means that this mechanism will also work on any blockchain, even blockchains that don't have a clock or don't have a reliable clock. And so this is actually a pretty elegant solution, and I'm very proud of it. It's something that our auditors were also very impressed by, and so I don't mind boasting about it at least a little bit. And so what we're going to do today is have a look at performing some of these trades in the simulator. So starting a pool with a small amount of tokens, performing an enormous trade in one direction, and then having a look at what the spot rate, EMA rate, inverse spot rate, and inverse EMA rates do as the protocol updates over time. So I'm going to stop sharing my screen. I'm going to hand it over to Mike to demonstrate that.
Great. Okay. So there are a few things.
Mike, are you there?
Yeah. Can you not hear me?
Mike, you're muted, by the way.
You're muted.
Yeah. Okay. Better?
Yeah.
Yes.
Okay. Good. So I want to point out a few things. One is that when you get into the repo and you look under examples, you'll notice that we have here the moving average example notebook, and this is going to follow precisely what happens in the BIP15 document, and with regard to the EMA section of that document. So we set up the system to match what's described in the document, and then go through the calculations which will generate these balances that you see. So anybody who is so inclined, I would encourage you to have a look at this notebook and give it a run through. You can see that basically the balances will match up between the different values that are stated. And am I looking at the right one here? I thought that I had some other screenshots in there, but maybe they're not showing up. But in any case, if you run this, I think that perhaps when you run it, the screenshots will show up again. With that said, going into today's section, we've got another notebook. I called it part 3 of 4 of the same user action state transition functions, even though, technically speaking, this is, just kind of a part of that, and kind of like focuses, solely on the EMA for today's section. To set up the system, we're going to do the same thing that we've done the past couple sessions and call our Bancor DAP class. We can read in, our price feeds if you want to kind of adjust those things. And the network fee, we'll set that at 0.15, which is the same value that Mark had it at there. And then we can just set like a low BNT minimum liquidity, our trading liquidity, so BNT trading liquidity and TKN trading liquidity for our just generic TKN token. We'll set it at 100 each, and then set the vault balance of TKN to 200, and the trading fees for both BNT and TKN. We'll give Alice, we'll create a new user, Alice, give Alice some balances in her wallet, and then we will enable trading. And so we can see here that basically our vault balance starts at 200. We've got our BNT and TKN amounts in Alice's wallet, and that is all as expected. So then at timestamp 1, if we have Alice make a trade, I'm just going to cancel that. At timestamp 1, Alice makes a trade for 10,000 BNT, and trading BNT to TKN. We can see that these values all start adjusting, and that our spot rate, right, kind of comes way out. Like Mark had mentioned, our EMA and inverse EMA are in line at 1 still. They're running behind, and we can make another trade for this time TKN to BNT on the next timestamp, and we can watch how those values change as well. And you can see here the 0.8 inverse EMA rate is obviously doing its job there, and if we call deposit after this, then we can see that basically we're able to prevent the attack that Mark had described by having these different user actions, which are always going to check the EMA and inverse EMA to kind of allow the actions to adjust balances or not. I know we're a bit short on time, so I'm going to kind of brush through a couple of things here towards the end, but I've included in the same notebook trade TKN to EMA function. If you call this, I believe that, I'm just going to say overwrite. If you call this function and you can get back the value that you need to perform this attack, right? So how much do you need to trade in order to adjust the EMA to a certain amount? And I'm just going to briefly show you where this can be found in the code base. So if you come into research, Bancor research and scenario generator, and you come into agents, you'll see within this class, we've got a bunch of like random actions that you can perform. So perform like a random trade, an arbitrage trade, and we can do like a force moving average, which is essentially the attack that Mark has been describing. So these functions are pre-built and kind of ready for you to make use of if you would like. You can see here force moving average, perform random EMA force trade, and so all of these are set up for easy use within the context of like running a Monte Carlo simulation, which is probably a bit more advanced than we're at in the current sessions. But I just want to point it out for anybody who maybe is just ready to fly through this as fast as possible. You can kind of jump ahead and get there, and otherwise, at the end of all the sessions, we'll probably do like an end-to-end, Monte Carlo run through, and we can review specifically the proposal of David Meister that we've already kind of modeled out using the simulator, and have a look at how those arbitrage trades and different attacks can be used within that context. So I think for today we're already a bit over time. So I'm going to call that wrap.
I think, if you don't mind me capstoning it just quickly.
Yeah.
While Mike was doing that, I just prepared a really quick chart to show people visualize how this works. So what I've done is, compared to the sheet that I started this meeting with, I've added the inverse spot price, which is obviously just like 1 over the other spot price. And then the inverse EMA works exactly the same way, same alpha value. It just uses the inverse spot rate to calculate itself. And then this column here is the EMA multiplied by the inverse EMA. Okay, and this is where I can really demonstrate the how this is detecting price manipulation. So the first thing is, this is just the 2 price charts, and I've depicted this on a logarithmic scale because you kind of have to. But here's the the spot rate moving up, and then you can see here's like the simulated flash loan attack. And then the gray line is the inverse spot rate and the same simulated flash loan attack. And then you can see the EMA for the Ford's reaction. It reacts very profoundly, to this to this exploit in retroactive time. But because it's linear, on the inverse spot, it barely reacts at all. And so when we multiply these 2 EMAs together, it should be approximately 1 all the way through, except when someone is attacking the price. And so that's what I've done here, right? This is the EMA multiplied by the inverse EMA. And you can see this just like clear as day, right? It's like 1, 1, 1 all the way through, nothing suspicious. And then as soon as the price manipulation attack is here, it's very, very easy to detect because of its departure from Unity. And so what this allows you to do is to basically set a profile, and this can be done either arbitrarily or, based on certain mechanics, where you can say we only trust, the price reported by the pool if the EMA multiplied by the inverse EMA is within a certain range. Okay, or you can treat these separately as we do in V3 and say that both of these need to be within 1% of the spot price for the EMA and the inverse spot price for the inverse EMA. But this is essentially the anti-exploit, the anti-exploit mechanism demonstrated. It is, it's time independent, which makes it blockchain agnostic, which is nice. And it's just a really unique, really effective way of doing stuff. And so I'm, like I said, I'm very proud of it. And, we've got the exploit functions built into the simulator if you want to screw around with it and see what it looks like when someone is performing an attack and convince yourself that the system is resistant to that kind of price manipulation behavior. And, how this